recording right now. Start the presentation. And I believe this should jump to where we were last time, where we were looking at the ionization of a particular peptide. Oh, there we go. Okay, so there we go. We were looking at this peptide last time. This is a tyrosine followed by a glutamic acid. YE is this peptide. This is read from the N termini to the C termini. And with this being read from the N to C termini, we've got N to C termini. At the moment, this peptide is displayed at a charge or at a pH of approximately 1, or, basically the lowest possible charge. And so what we're going to do with that is we're going to have our first question about this peptide, or first question for the day. Select the charge that this peptide cannot attain. Okay, so I'll jump back, take a look at it for a moment. And here we go. Start the question. And you've got 50 or 60 seconds to answer this question. Another way, it's the peptide YE, or yay. Yeah. Oh, it did stop. Ten seconds left. Right. Let's check out our responses for this question. It is closed. 43 people marked that this peptide could not attain a +2 charge, and that is the correct answer. So if we toggle back to this peptide, this is what it looks like at a pH of 1, 0, 0.5, 1.5. Really, this is what this peptide is going to look like until you reach a pH of, or the predominant form of this molecule looks like this until you reach a pH of 2.1, when then only 50% of the molecule looks like this. So this is basically a molecule that can be deprotonated. The way it's displayed right now, it has a charge of +1 because this is the only positive charge. Now, there are groups on here that are polar, but that's all that there are. Or sorry, that's what they are in addition to what we see. Okay, so now let's go on to our amino acid chirality. So just like sugars, where you have your L versus your D configuration of a sugar, amino acids have the same sort of opportunity. They have that same levo and dextro rotary based on how they rotate polarized light. And so the convention, whenever you're drawing an amino acid, is to draw and understand that the L configuration is the biologically relevant form of it. So L-serine displayed here with your amino group on the left-hand side. Now, typically, what I'm going to do is I'm going to write it or draw a molecule with my carboxyl group on the right-hand side. And that's just because whenever you're writing out a peptide or a polypeptide, multiple amino acids coming together to make one large molecule, then you'll have this opportunity to basically write it in a kind of straight line. Whereas if you were to make a peptide bond coming up from here, well, then your molecule is going to be very jumbled. So your peptide bond would effectively be here, then your alpha carbon would be here, and then your carboxyl group would be right here. Then your next peptide bond would be here, your alpha carbon would be here, your carboxyl group would be here. And so it's just going to it's going to visually kind of cannibalize itself, and that it's not going to be very easy to discern and very easy to process. So that's just kind of a convention whenever you're drawing a peptide. But the important takeaway from this is that your L configuration of an amino acid is the biologically relevant form. Now, another property that amino acids have that's very important for um, basically measuring protein function or measuring the presence of protein, is that, and this is something that if you've ever quantified DNA, if anyone has ever done a genomic DNA extraction, then one of the things that you do is you measure the amount of protein that is recovered as well as the amount of plasmid or genomic DNA that's recovered. And what you're going to do is you're going to measure the amount of light that's absorbed at 280 nanometers. And you're going to measure that because of the fact that your aromatic amino acids, they absorb light at approximately 280 nanometers and at 260 nanometers. The amino acids tryptophan and tyrosine absorb the most light at 280 nanometers. Phenylalanine doesn't really absorb much, if any, light there, but it does absorb at 260. So this is important and this is valuable because one of the things that it means is that if you have like if you're doing like urinalysis or something like that in a hospital or clinical setting, you can measure A280 and you can determine a concentration, or you can make a rough approximation of the concentration of protein that's in, urine or something like that. And that could be an indication of, I believe it's kidney failure whenever protein begins to accumulate in the urine. So this is very helpful because of that kind of diagnostic tool. Now, another property that's very important to understand about amino acids is the amino acid cysteine. It's one of two amino acids that has sulfur in it, the other being methionine or MET. Now, methionine has a sulfur group or has a sulfur atom, but it looks like this, S-CH3. So that methyl group, so you got a CH2 and then a sulfur, and here's the rest of the polypeptide, or here's the rest of the amino acid. This methyl group, the presence of this methyl group makes methionine. It takes it from being a polar amino acid to a non-polar, NP. Cysteine, by contrast, has this thiol group or this sulfhydryl group. Now, the significance of that is dating back to Gen Chem 1. If you think about where is sulfur on the periodic table, well, it's in the same column as oxygen. So what that means is that this sulfur has some lone pairs of electrons. And so this group, this R group right here is, well, it's polar. It's very similar in structure to, now thinking about your 20 proteinogenic amino acids, which amino acid has CH2, then OH as its R group? Serine. So cysteine that's right. Serine is very similar to cysteine in terms of their polarity. Um, and one difference or one distinction between serine and cysteine is that serine, with having an oxygen, can participate in hydrogen bonding. Cysteine can't participate in hydrogen bonding, but it has that lone pair of electrons, so there's some weak interaction with its environment. Okay, now, oh, that's there we go. And so here's our last question for this material. Which other amino acid other than cysteine has sulfur in its side chain? All right, let's 65 people answered. 60 people got it right. So I was just mentioning that methionine is the amino acid. Celestine is not an amino acid. Histidine, well, it's got a ring, but it doesn't have a sulfur in it. All right, I believe that this is the, oh, almost. Our final slide for this presentation is all about the interactions that different amino acids can have. Now, one thing that I want you to recognize about these two amino acids right here is, well, it's just a bunch of hydrocarbons. Add to the chat what type of interactions do you think are going to take place between these two amino acids? Dispersion forces. We're going to see with these the hydrophobic effect in play. What about these two? Tyrosine and an asparagine? Absolutely, Kate, that's right. Hydrogen bonding. We're going to see hydrogen bonding between these. Not the hydrophobic hydrophobic for here. Hydrophobic. But this will be, I mean, if you wanted to classify it as another way, you could say hydrophilic. But this is going to be hydrogen bonding between these two. Bonding. So the um, the hydrocarbons, they're going to basically force away any sort of water because they just want to be close to one another. Those London dispersion forces will facilitate that. Then last but not least, these groups right here, which really, I mean, the most part that you care about is this small section right here. What type of interaction is going to take place between those groups? Got negative. Yeah, absolutely. Ionic interactions. That's a great question. So, it wouldn't be peptide, or this wouldn't be a peptide bond that's formed. Um, Instead, what you're going to see with these is you're not going to see a peptide. You're not going to see like an additional peptide bond form because they're basically not going to get in close enough proximity between hydrogen bonding or ionic interactions between these two right here. So this would be, it's ultimately going to be ionic because your ionic bonds are going to be stronger than those hydrogen bonds. Now, that's a great observation and great question about, well, why isn't it a peptide bond? And that's just because the peptide bond that exists between or within this polypeptide is going to prevent those groups from getting close enough together. All right, so this is going to wrap up. Okay, I'm going to pause my share while I go open up, or that wraps up the stuff from the other day. Now And while I'm talking, one of the things that I wanted to say is that um, one of the things that I want to say is that we've got uh, top hat questions that we're doing during class. I got an email the other day from someone who was curious about, well, why am I not opening them up for 24 hours? And I'm starting to do that as of today. So there will be top hat questions that are set up as homework. They are the exact same questions that we're doing during class. You do not have to do the homework top hat questions. That's for people who are taking who can't make it to class. Those questions have to be answered within 24 hours of the class period, though. And with that said, top hat's just going to be graded based on completion. And so, did you answer the questions, yes or no? So if you're here and you answer the questions, then great. If you don't make it to class, I'm going to be posting the recording, answer those top hat questions before 24 hours after the class is done. Okay, so next up is unshare or unpause. Now we're talking about protein structure, primary and secondary structure. So this is, we've got protein structure and different levels of protein structure. This visual down at the bottom, I think, really does a great job of illustrating it because we've got our different kind of levels or our progression. Our primary structure is just the amino acid sequence in a polypeptide chain. So you would see a primary structure using the three-letter codes, LYS, ALA, HIS, GLY. You could also see that listed as L, A, H, G, K, K, V, L, G, A. So you list this in the N termini to C termini direction, which is why whenever I'm drawing a peptide or writing out a peptide, I'm going to write it N, C, C, N, C, C. Now, that primary structure is going to be stabilized by it's just the sequence and it's stabilized by peptide bonds, so covalent bonds. Your secondary structure is this right here. One example of a secondary structure is a alpha helix. So the secondary structure are commonly referred to as local structures because they are kind of confined to smaller regions of the polypeptide. Because keep in mind, you might have a protein that's 700 amino acids. You might have a protein that's 1500 amino acids. And your secondary structure is going to be basically comprising amino acid, you know, let's say 35 to 45. So that range of amino acids might be involved in forming a local structure. We're going to dig into those individual local structures after a little while. Now, the tertiary structure is the overall 3D shape of a single polypeptide. And that's a very important thing. Only one, I'm going to label it as PP, peptide or polypeptide. So if you look at model C here, this is a 3D fold of a protein. Whenever I think about and try to visualize a protein, I always get a piece of paper and I crumple it up and I say, this is a protein. It has a unique shape. Now, there are proteins, maybe you've heard this terminology before. You've heard proteins falling into two major categories of globular and fibrous proteins. Globular proteins, they have these kind of wild shapes, whereas a fibrous protein has a more uniform shape and they have a more uniform primary and secondary structure. Now, your last level of protein structure, which is the quaternary structure, is when you have multiple, and I'm going to label it as 2 plus polypeptides, 2 or more polypeptides that fold together. So if you were to imagine, I always like to get, like I said, a piece of paper. So here is a single index card that's been folded into one 3D shape. These are two independent proteins that each have tertiary structures. When they fold together, they kind of find grooves that match up with one another. This is the quaternary structure of a protein. So The what's important to know about all these different levels is what are the forces that hold them together. Now, your primary structure is going to be held together by covalent bonds. Your secondary structure is backbone H bonds. Your tertiary structure, well, basically I'm going to capture it all with R group interactions. So we spent a good bit of time on R groups and classifying them as polar or non-polar, aromatic, polar positive, polar negative. So that's where this all comes into play. Now, some amino acid R groups can interact through hydrogen bonds, others can interact through ionic interactions, and then last but not least, covalent interactions in the form of two cysteine residues. Now, with all that said, this one, so this R group interactions, basically your covalent and your non-covalent interactions are going to stabilize the tertiary structure. Now, your quaternary structure is effectively the same thing, but it's where you have multiple polypeptides interacting. So, are there hydrogen bonds that can stabilize a quaternary structure? Yes. What about ionic interactions? Absolutely. There's numerous different types of interactions, but essentially the difference between the tertiary and quaternary structure is really just that you have different polypeptides involved, or you have additional polypeptides involved. All right. Now, they're all okay. So thinking about those different levels, at what structural level is the amino acid arginine's R group ability to form ionic interactions significant, given these options? Does the R group of arginine impact the primary, secondary, or tertiary structure? Okay, 10 seconds left. All right. 57 responses. Awesome. Let's take a look. Tertiary structure was the most popular answer, and that's absolutely correct. Now, one of the things that people have a tendency to get mixed up on is they think, oh, okay, well, the R group, well, that's only going to be there if you have the primary and secondary structures there. And you're right. But when you think about a primary structure, that's amino acid followed by amino acid followed by amino acid. There's virtually no significance to the identity of those individual amino acids. So the identity of any amino acid doesn't impact the primary structure. The secondary structure, those are backbone interactions. And so the R group is really not a big factor when it comes to stabilizing the secondary structure. So there we go. Now, I like this figure right here because it visualizes everything. Because we've got our helical structure where this ribbon is simply our helix or our backbone, and then those dashed red lines are those hydrogen bonds. Now, when you think about the backbone of an amino acid and a polypeptide, you have your amino group and your carboxyl group. So it's hydrogen bonding between those groups. Your amino group acting as a hydrogen bond donor, and the carboxyl group acting as a hydrogen bond acceptor. Now, the helical structure is one of the secondary structural elements. Excuse me. Another very important secondary structural element is known as a beta sheet. So alpha helices and beta sheets are your two major um, secondary structures. Now, you can see those are hydrogen bonds that stabilize those. In the remaining portion of this figure, we've got different levels stabilizing them. So our tertiary and quaternary structure. Um, Tertiary and quaternary structure are going to be stabilized by other interactions. So here what we have is our hydrophobic interactions, and then we've got disulfide interactions between our covalent or our covalent bonds between our cysteine residues. Your electrostatic interactions between, well, that could be a lysine and an aspartic acid that stabilizes those, but also you could have side chain hydrogen bonding. And then here's one that tends to kind of slip people's minds. I know it slipped my mind. And that is metal ion coordination. You could have two, well, let's see, you could have a aspartic acid, a magnesium ion, and a glutamic acid. So those two R groups, by virtue of them being able to be involved in ionic interactions, can kind of be stabilized across from one another. So covalent bonds help stabilize which level of protein structure? About 10 seconds left. 5, 2, 1. Closed. And let's check out. So we're talking about covalent bonding stabilizing which levels? Well, we know it's going to stabilize the primary, but we also have the tertiary structure. The reason that we also have the tertiary structure is because you can have a disulfide bond. So it's going to stabilize the primary and the tertiary structure. Now, if this question were worded where covalent bonds exclusively stabilize which level, well, then it would be primary only, or this is the only force that stabilizes this level. Tertiary structure, you have your kind of mix of almost every single different type of interaction that helps stabilize it. Now, we looked at a peptide bond the other day formed by a condensation reaction. Peptide bonds are extremely stable. Now, anytime you see a figure like this, I think that it's always very important to kind of like put your brain in the right context. Okay, so here is the N termini of this individual amino acid 1. This is our alpha carbon. Here is our C termini, and that C termini forms our peptide bond with the N termini of our next amino acid. Now, those covalent bonds are super strong. Sorry, let me rephrase that. They're extremely strong. They can be broken whenever they are exposed to a strong acid or a strong base at a high temperature. And usually what this means is about 6 molar HCl as an example. And you're heating it up to like 95 degrees Celsius. So proteins are pretty darn stable. Now, with that, peptide bonds are they get that stability from peptide bonds or that peptide bond backbone. Now, the structure of a peptide bond is kind of interesting because really it's resonance stabilized. And a peptide bond with these two different resonance structures, it actually has partial double bond character, which makes it strong, but also makes it fairly rigid. So it really doesn't move a whole lot. Now, with that said, I was showing you this as like, here's a model of what a protein does. It forms these crazy 3D shapes. That's absolutely true. But what that means is basically the other bonds that are adjacent to either preceding or succeeding the peptide bond is where some sort of rotation is going to take place. Now, like I said, when you get a figure like this, you always want to be able to identify your alpha carbon because that's going to help you identify your peptide bond. Now, whenever you identify that alpha carbon and that peptide bond, one thing that's important to remember, regardless of the pH, a peptide bond is going to be uncharged. Now that's a net that it has no charge. So whenever we draw a peptide, and actually when we looked at that peptide YE, if you notice the peptide bond had no charge, and that's why we didn't account for the N termini and the C termini of the pKa values. We didn't account for those because that peptide bond isn't going to be ionized. It's not going to be protonated or deprotonated. Now it's going to have partial charges, in which case it can participate in hydrogen bonding, but that's about it. Now, the structure of the peptide bond was first described by Linus Pauling in 1939, and Linus Pauling would go on to continue having a fantastic career as a scientist. And proposing the triple helix of DNA, which ultimately was disproven because of Rosalind Franklin's work, but he was an earth mover in terms of life sciences. And if you're ever interested in Linus Pauling, I believe it's at Oregon State University. They have the Linus Pauling Institute, where one of the things that they study is they study um, vitamins and minerals. Because later on in his life, Linus Pauling got very interested in mega dosing of vitamin C, believing it to be a, kind of a cure-all of sorts. So back to the peptide bond. It's a planar kind of molecule. Now, due to the double bond character, the six atoms of a peptide bond group are always going to be planar. So here's our peptide bond, and that's going to be like this. So each one of these little squares, I always try to visualize them as my palms. Each square is the palm of my hand. So there can be rotation about these. So each of my hands can move independently, but my palm itself is going to remain as a flat plane. Now, this is important because it's these rotations that get us a structure that looks like this, where we have a 3D model of a protein. This 3D model or this 3D structure is attained despite or in spite of that peptide bond remaining as a flat plane or a part of a flat plane. Now, the rotations that can take place around a peptide bond. Twists can occur about either of the bonds linking the alpha carbon to the other atoms of the peptide backbone. Okay, so I think that again, I'm going to go back to draw and I'm going to shade in my peptide bond just to give you some familiarity with that. Okay, so going from here to here, carbonyl to amine, carbonyl to amine. These are my peptide bonds, carbonyl to amine. Now, I can have my other bonds adjacent to that where I have some rotation. So what that means is where my middle fingers are meeting, that's effectively this bond right here or this bond right here. So we can have this rotation. Now, like my palms, I'm not extremely flexible, but if you look at this hand, it's my right hand, I can rotate it, and that's kind of the limitation that I have. Now, that limitation is largely dictated by my hand being connected to my arm, being connected to my torso and everything. But I think that's a good model for visualizing a polypeptide. So this can only rotate so much until there's torsional strain on my arm and the rest of my body. Of course, I'm not a circular peptide, but then I can, let's see about rotating in the other direction. Well, I'm less flexible in that direction. Now, that all comes back to is each one of these bonds, they have different rotations. And that's very significant because there are bond angles and there are two angles per peptide plane. I always think about this as, and I label them, I identify them as N to C is my phi angle. C to C is my psi angle. So whenever I write out a polypeptide, N, C, 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 this will be my phi or phi. I don't know anyone who says phi. Well, I think if it's in like Greek life or something. So that's a phi, and this is my psi. The bond that doesn't have a label is my peptide bond. Okay. Now, this rotation and these angle combinations are really important because what they show us, or what we can use them for, is predicting structures. So here's our definitions. Our phi angle describes the rotation about the N to C bond, and our psi is our C to C. Our phi is N to C alpha, and our psi is C alpha to carbonyl. Now, we can have a certain set of combinations of those bond angles. And so the rotation that this can take on and this can take on, there are certain combinations that are favorable, much like my palms. They can both rotate in this way. So if I'm looking at this as like this is my starting point, I would say this is a 90-degree angle. This is a 90-degree angle. This would be a negative 90. This would be a negative 90. So I'm rotating in certain directions and to certain degrees. A Ramachandran plot is a plot that shows what are favorable bond angles. Now, this shows us the combination of our psi and our phi angles, basically the appropriate ones where there are energetically favorable combinations. Now, when you look at and visualize a Ramachandran plot, this white area, all of the white area is where you are not going to find a favorable combination. So when you look at a Ramachandran plot, what it's telling you is not only is something favorable. So if we look at a psi angle that's negative 90, and let's go with 60, positive 60 for a psi angle, that would end up right there. That's a favorable combination. Whereas if we go positive 90 to positive 60 out here in that white area, that's an unfavorable combination. Now, what this is also helpful for is whenever a protein folds into a secondary structure, you can find the combination of bond angles that are most likely to appear there. So that's the benefit of a Ramachandran plot. Now, some values are more likely to be present than others. So as you can see, psi angles that are typically negative 90 to negative 180, that's a good combination of those bond angles. Unfavorable bond angle combinations lead to orbital overlap and basically torsional strain in something that's not really energetically stable or attainable. Okay, so all that leads to a conversation about secondary structure. Like I said, I mentioned there were two major groups. Oh, what is the difference between the blue and the green regions? Those have to do with secondary structural elements that are formed. Sometimes you'll see this is a more detailed Ramachandran plot than you'll find in other locations. And so this highlighting this particular region versus this right here. Mostly what you're going to find in this blue area are going to be your alpha helices, alpha helix, or no, that would be beta sheets. Sorry, beta sheets.
She doesn't really say what the meaning.
Okay, let me. So that's beta sheets there. Oh, dang it. My eraser's too broad. So beta sheets. And then this area and this area, those combinations, the ones that are the arrows, those are specifically highlighting one designation of a beta sheet or two different designations. They're known as parallel and anti-parallel beta sheets. That's a great question, Morgan. Thank you for that. So that's it's distinguishing between secondary structural elements is the color pattern there. Okay, so I mentioned that there are two major secondary structural elements, and there is actually a third, but it's a little bit less kind of, I would say, dramatic. It's kind of an inherent part of the other because, and we'll get into it in a second. I'll talk about the beta turn in just a little while. But your two major secondary structural elements are the alpha helix and the beta sheet. There's also a beta turn, but that's, like I said, it's kind of it exists because the beta sheet exists. Now, the driving force for the formation of secondary structure is the formation of hydrogen bonds on the peptide backbone. So your amino and your carbonyl groups are the groups that are going to establish these hydrogen bonds. So this is all independent of the R groups. So at this point in time, we're looking at a polypeptide as amino acid, amino acid, amino acid, amino acid. We don't care that it's arginine, lysine, alanine, or anything like that. We care that it's just amino acids. These are referred to as local structures because it's almost like here is the 3D structure of a protein, but this right here, this little fold would be an example of a local structure. There's a protein that could have a single alpha helix, and that's it. It doesn't have to be one massive alpha helix. Instead, it's just like, comprised of 10 amino acids. So your local structures also involve fewer than your entire polypeptide because your polypeptide might be, 800 amino acids and 10 amino acids would make up an alpha helix.
Anyway,
Now, protein structures, the questions were being asked about them back in the 1930s, and William Astbury discovered fibrous proteins studied fibrous proteins rather than globular proteins. He studied fibrous proteins um,
that year was 28.
using X-rays to determine diffraction patterns. Astbury showed that there were drastic changes in diffraction of moist wool fibers compared to when they're stretched. Unstretched showed periodic repeats of between 1.5 and 5.1 angstroms. Now, an angstrom is, I think it's 10 to the negative 12th. It's smaller than a millimeter, smaller than a nanometer, smaller than a micrometer. And an angstrom is basically a measurement that's regularly used on the atomic level. Now, a stretched wool fiber showed repeats of 3.5 and 7 angstroms. Okay, so we have these continuous repeats. Astbury proposed that the unstretched protein molecules formed a helix, which he called the alpha form. Stretching caused the helix to uncoil, forming an extended state, which he called the beta form. Astbury was also the first to propose that main chain hydrogen bonds had a role in stabilizing protein structures. Now, Linus Pauling is credited with discovering the alpha helix, and even though the amino acid was known, or even though the structures of amino acids were known, the structure of proteins eluded any sort of description. Pauling constrained the structure of the peptide bond. And so they went with this idea that it was a planar, rigid molecule and basically applied that with this idea of an alpha helix as the helical structure and an extended or beta sheet structure. Now, what I want to focus on here is let's look at an alpha helix. So an alpha helix, I'm going to populate this slide with everything that I need. Okay, there we go. So when you see this right here, this is our polypeptide drawn as a linear molecule. Well, that linear molecule, we've got a carbonyl group, we've got an amine. We've got another carbonyl, we've got an amine. We've got all these groups that can act as hydrogen bond donors and acceptors. Now, in this particular molecule, this linear molecule, the proposal is that this linear molecule folds into something that looks like this. So it's almost like you have this straight chain polypeptide right here, but what it's going to do is it's going to wrap up on itself. And I know that I've taken my 3D protein and shrunk it down, but essentially, if you put this molecule right here as a linear molecule into a solution, well, there are going to be forces that cause it to fold up. And what that's going to lead to is this alpha helix. So ultimately, individual parts of this alpha helix were measured and given approximations on the size. Okay, so this rise, that's a term that I want you to be thinking about because this alpha helix is taking place in 3 dimensions. So we've got our X, our Y, and our Z plane that we're thinking about. So when we account for and think about a single amino acid, we want to think about how tall it is and how much space that it takes place, or how much space that it occupies. And the rise per turn is approximately 1.5 angstroms. So 1.5 angstroms. Now the pitch or rise per turn is 5.4 angstroms. So that means that in order to start from, or to go from here to here. So imagine, I think that it's easiest to think about a spiral staircase. So if you and your friend are standing on a spiral staircase and you go all the way up and you're standing right above your friend on that spiral staircase, you've walked up and around. The height between your friend and you would be 5.4 angstroms. Now, the great question there is, well, how many amino acids would it take to make that one rotation? And the answer to that is, well, approximately 3.6. So what that means is that in one complete rotation of that spiral staircase, there's approximately 4 amino acids, roughly. That 3.6, that 4, that's a rough average. I want you to keep in mind 1.5 angstroms, 5.4, and 3.6. Now, this last item, on average, there are 10 residues per helix. Okay, so add to the chat how many rotations are there in the average helix. If the average helix has 10 residues, what's approximately the number of rotations in the average helix? I've got a vote of 6, 6 to 7. Okay. So essentially, let me clear some of my drawings.
What?
This is this is always a tricky one. Here's one amino acid. Here's another in the background. Then here's another, and here's another. I thought 3, maybe I don't. Okay. So we're looking at about 3.6 amino acids per rotation to go from here to here. About 3.6 from there to there. Okay, so then how about to go from here to here?
And I changed it to how to use because that's basically what we're doing.
So if it's 3.6 to go from here to 3.6 amino acids, then here is 3.6 amino acids. That would be 7.2. And then, well, we've got about 10.
Oh, that's what I'm saying.
So we've got one rotation, a second rotation, and then 3.6 AA for our third rotation.
Yeah, exactly.
Okay. Now, this is definitely something that is it's abstract. It's tough to wrap your mind around. Um, what I'm going to do is we're going to pick up with this on Friday. And so I'm going to go ahead and stop my recording